We have been discussing basics of quantum mechanics. Am I audible?
Yes, sir.
Yes, sir.
Yes.
Okay, so we have been discussing basics of quantum mechanics. Um, we are basically discussing going to discuss two uh, specific examples. One of the example we started yesterday. Um, the purpose of this example is to show you that how we can solve space part of the or time independent part of the Schrodinger equation. Okay, you remember Schrodinger equation has two parts. One is space part. If you use the separation of variable technique, you will you will be able to reduce. I mean, you will be able to reduce the equation or arrange the equation in such a way that there will be a space part and or a time independent part and a time dependent part, right? So this time dependent part we have solved, and so this is the time dependent part and this is the time independent part. So this will be equal to the constant, that is total energy, or a constant capital A we considered yesterday, and we solved this part and found that phi t is equal to exponential I exponential minus I e over h line t, right? And we have also considered this wave function, which is function of x and t, for using separation of variable technique. We considered it is a product of space term and time term. Okay, time dependent term we have found this way. Okay, space dependent term, for the space dependent term we are going to see, or we are going to solve two examples. But in the exam you might come across with some other we might give you some problems where you have to identify similar boundary condition and solve this space dependent part, right? So all we have to do, we have to find psi x, and if we find psi x, then psi x multiplied by phi t, that is e to the power minus I e over h line t, will give us total wave function, okay, or expression for the total wave function. Now, yesterday we started with our first example, which was 1D infinite square well, okay, or 1D infinite potential well. And in that 1D infinite potential well, we considered it is a one-dimensional well, okay. So that the distance, the dimension of the well is L. So 0 and L are the two walls, and the potential barrier, as it is an infinite potential well, is infinity. So a particle of mass m is free to move inside the well, okay, but outside it can't go because it is a forbidden region, right? Because the potential barrier is infinite and the energy of the particle is much less than that. So particle is free to move inside, and you remember we wrote some boundary conditions. Okay, what are the boundary conditions? One of the boundary condition was ux equal to 0, that is potential energy associated with the particle is 0 inside the well. Okay, so that is for within the well, and it tends to infinity because in other places, right? So this was the one boundary condition. So there are other boundary condition we also considered, which was psi x equal to 0 and psi x equal to L equal to 0, because here and here the wave the particle can't go in this forbidden region because it is infinitely confined with infinite potential barrier. So the particle can't go outside. So there should not be any wave function outside this potential well. So if there is no wave function outside the potential well, that means at x equal to 0 the wave function should be 0, and x equal to L the wave function should be 0. Okay, because you remember we mentioned that wave function is continuous. Okay, wave function is continuous, so wave function here has to be 0 here and here, so that outside here also it is 0, right? So these conditions I have assumed, and we solved the time independent part of the Schrodinger equation yesterday. Okay, what was the time independent part of the Schrodinger equation? This was the time independent part of the Schrodinger equation. We considered this ux term equal to 0. So this part we equate it with E. Okay, and then we found out the solution, and the solution can be written as a sine kx plus b cos kx, right? And we use these boundary conditions, for example this boundary condition, and find that b equal to 0. Okay, and then we use this second boundary condition, okay, psi x equal to L, and ultimately found that psi x equal to a n pi x over L, right? And we said that from there that kn is quantized, right? I hope you remember these points. I am not I don't want to discuss it again elaborately. And also we found out that the value of a is the constant, okay, and the value of a this turned out to be root over 2 by L. How do we find it? Using probability density function. Okay, you remember we use this integral. Okay, psi star dx equal to 1, right? And we put the equation. What is the psi? Psi is a sine n pi x over L. So we use this, and we find out this integration, and we find out the value of a. Okay, and that turned out to be a equal to root over equal to root 2 over a, right? So this part we have done, and at the end of the class what did I do? I tried to draw the wave functions, okay, for various values of n. You remember? So if I try to draw the wave function for various values of n, so this is 0 to L. Okay, so we said this is n for n equal to 1. So if you put n equal to, so you see the final solution was small psi equal to sine n pi x over L. Okay, n can't be 0, that we told yesterday, because if n equal to 0 then it will give you a trivial solution, right? N can't be 0. So n can be 1, 1, 2, 3 and so on. If n equal to 1, you see you will get sine pi x over L. So if x equal to 0, the wave function will be 0. If x equal to L, the wave function will also be 0 again. Okay, so you will get waveform of this sort, and in the next half the waveform will be like this, right? Similarly, for n equal to 2, you get waveform like this. Okay, and in the next half you get waveform of this type. But you remember that the amplitude is same for all values of n, so you will get same amplitude waveform. Okay, but the periodicity will differ based on, because the periodicity will differ because it depends on the value of n, right? Now this part we have discussed. We have also said that we can redraw a similar waveform in energy diagram. Okay, so if I try to put similar waveform in the energy diagram, okay, then we can draw for, say, E1, that is the ground state energy level. Okay, So this is for say E1, okay, for n equal to 1. For n equal to 2, you will have higher energy, right? Because you remember what is energy is also quantized, and what is the formula for energy. Formula for energy is h line squared kn squared by 2n, right? So energy is also quantized, and kn is n square pi square over l square, right? Kn square is, so we will get this is your energy. In other words, as you increase n, square of n will give you energy. Okay, so this is E2 will be 4 E1, E3 will be 4 9 E1, and so on, right? Because it depends on n square. So this is say n equal to 2, this is say n equal to 3, and corresponding waveform you can draw like this, right? And so on and so forth. So this is the way you represents your waveform. You see the waves we are getting here is kind of a standing wave, similar to what we get in when we try to oscillate a string. Okay, a standing waveform we are getting, oscillatory waveform. And but however, I mentioned in the last class that it is very important to get chi square or chi star, because that's the probability density, and if we get probability density, then we can tell that how much probable for the electron or for this particle to be a particular position at a particular time, because it is better to express it in the probability form, because then we can basically measure. Okay, so how we can find out the probability? Probability we can find out if we can calculate chi star. So this is say chi star, okay, or chi x square, whatever way you put chi star. So that's the probability I am plotting. So this is x equal to 0, x equal to L. So this is for n equal to 1. Say this is for n equal to 2. N equal to 2, you will get like this, because you see it will not be negative, unlike chi can be negative. Okay, but here as you are plotting chi stat as the probability density, you will not get negative term. So if you keep on increasing n, okay, for very large value of n, say n tends to infinity, okay, you will get probability density something like this. Now, so in case of classically, if you think about it, in the potential well, that particle is randomly moving. Okay, so the probability of finding the particle is uniform, in the inside the well, right? But in case of quantum mechanics, the probability of finding the particle is not uniform. Okay, uh, because there is the energy is quantized. Okay, and if you find the probability density, you will see that for n equal to 1, probability of finding the particle is maximum at the center. Okay, and then minimum near the wall. For n equal to 2, probability of finding the particle is minimum here, and minimum here, whereas it is maximum here and here. Okay, so if you keep on increasing the value of n, for n equal to n tends to infinity, n is very large, you see probability of finding the particle is almost uniform over the between 0, x equal to 0 and x equal to L. So as we move, as we go for higher and higher order of n, it is basically approaching to classical concept. Okay, so let me repeat it once more. According to the classical mechanics, the probability as the particle is free, particle can have any energy. Okay, and the particle can have the probability of finding the particle inside the well is uniform. Okay, it can be here, it can be anywhere inside the well and with equally probable. Okay, but this is not the case in case of quantum mechanics, because here energy is quantized. Okay, energy and momentum is quantized. So what we are if you plot the psi star, you will see that at some point it is maximum probability of um, uh, having the particle there, and in some places it is minimum. For example, n equal to 1, at the center of the well it is maximum, and at the side near the side walls it is minimum. Okay, similarly for n equal to 2, at the center it is minimum and also at the side walls it is minimum, but here and here it is maximum. Okay, at a distance say l by 4 it is maximum, and 3l by 4 it is maximum. So similarly, if you keep on increasing value of n, at some point you will see that the probability of finding the particle is almost uniform between x equal to 0 and x equal to n. So for n equal to n very large, you will have like close to that of the classical approach, right? What else? Now, so this is the phi term, you remember, and this is I omega and t, that is the, so this is the space or time independent term, and this is the time dependent term. Okay, because time dependent term, you remember, e to the power, let me just go back. Yeah, e to the power minus I, e over h line, e over h line is basically omega t. So E is quantized, so I am writing omega n. You see, so you can write En over H line. That is also okay. I am writing because this is nothing but, we saw it, En over H line, right? So En is omega n H line. So I omega n minus I omega n t. That is the time dependent part, and this is the space dependent part. Okay, so this is a spatial, and this is the temporal part or time dependent part, right? So this is the solution for the entire total wave function. You can also write it in a little bit different manner. I hope I am writing it correctly. So this is, this you can, if you sin knx, if you write it in the form of e to the power, then you will get this. So you see that two waves propagating in the opposite direction and forming a standing wave, right? So in a nutshell, what I want to briefly say is that energy associated with the particle is quantized. Okay, in infinite potential well, and ground state energy can't be zero. Okay, unlike in the classical approach, the minimum energy can be zero, and for each quantum number n equal to 1 2 3 4 and so on, we will have the standing waves, and for very large value of n, the humps are very close to each other. Here you see the humps are very close to each other, and so you will get similar to that of the classical concept. So probability of finding the particle becomes uniform if you go for large value of n. So this is our infinite potential well. Let me talk about briefly about finite potential well. Okay, so this is our example number 2, that is finite potential well. So in case of, In case of finite potential well, say this is region 1, this is region 2, and this is region 3. Okay, x equal to 0 to x equal to L. Now say this is, say I'm just randomly choosing, say this is the energy or the kinetic energy of the particle inside the well. Okay, and say this is my u naught, that is the height of the potential barrier. Potential barrier height is u naught. Inside the potential well, as there is no other particle and no other force inside the well, we can consider that the potential inside the well is equal to 0. Okay, so that is, so this is for region 1. Okay, and ux equal to u naught for x less than 0 and for x greater than L. So this is for region 2 and this is for region 3, right? So this is the boundary condition. So if we again, so as I said, like our purpose is to solve the special part of the Schrodinger equation. Okay, so if we solve it, which equation I have to solve? This is the equation, you remember, d2 psi dx2 plus ux psi x equal to e psi x. So this is the equation we have to solve. Okay, in other words, we can rearrange it a little bit. d2 psi dx2 equal to 2m h line square ux minus e psi x, right? So this is the equation we have to solve for the special part. Now the thing is, if we think carefully, what is the general solution of the of such a differential equation? Okay, general solution is, let me write the general solution because that will then help you. Say this is a differential equation of the similar form which we have written here. Okay, d2f dx2 plus equal to bfx. Now then the solution fx will be a sine, you remember what is the solution we discussed in the first example? Okay, a sine kx plus b cos kx, right? So that was like k square x. I write it today, can't remember. No, we haven't. So in yesterday's class, if we, let me see if I can find it out. So you see, in yesterday's class we have discussed this infinite potential well, and this is the ultimate equation we solved. D2 psi dx2 is equal to minus k square psi x, and we get this solution, right? Similarly, the similar thing I am trying here today. Okay, I am just writing a, so that was like k square. You see. So So if we write the similar expression, okay, a sin kx plus b cos kx. So here it will be a sin root over bx plus b cos root over bx, right? And this is for, you remember, b less than equal to 0, right? So if b more than equal to 0, what will be the solution? B greater than 0. If b greater than 0, the solution will be a e to the power, I hope these are known to you, okay? So for b greater than 0, this will be the solution, right? So what is b? B is equal to 2m h line square ux minus e. You see, 2m over h line square ux minus e is b. Okay, so that is the b. So if b greater than, b less than 0, this will be the solution, and if b greater than 0, this will be the solution, right? Because we will see in both the cases, we will I mean, both b less than 0, b greater than 0 will appear in our solution of this equation in when we try region 1, region 2 and region 3, right? In region 1, you remember ux equal to 0, because inside the well ux equal to 0, there is no other particle, no other force, okay? So the potential inside the well is 0. So ux equal to 0, that means we can write b equal to minus 2me by h line square, right? So that is, you remember that we can put k square, and so the equation will become d2 psi x dx2 equal to minus k square psi x, right? So psi x will be similar whatever we have discussed in our infinite potential well. You remember, a sin kx plus b cos kx. But here, so this will give you oscillatory solution, and here a and b both are non-zero, because unlike in the infinite potential well, here we can't consider that psi x equal to 0 at the wall. That we can't consider. That we have considered in the case of infinite potential well, right? So here psi x, for finding a and b, we can't consider psi x equal to 0. We have to take other boundary conditions, okay, contrary to infinite potential well, where out of a and b we found that b equal to 0, right? So in case of region 2, so let's assume it is x equal to 0, okay, and this was in region 1, means x greater than 0 less than L. So that's region 1 inside the potential well. And here say x less than 0. Where is x less than 0? X less than 0 is region 2. You see here, this part, right? Now here we can again rewrite the expression. Here what is the value of ux? Ux will be equal to u naught. You remember, ux will be equal to u naught, because potential over there, height of the potential is u naught, and we have considered that E less than u naught. Okay, we know that is the energy of the electron, or energy of the particle. E is less than u naught, because E is less than u naught, right? Because the particle is inside the well, and we are considering the energy of the particle is less than u naught. I mean, the particle energy might be more than u naught also. That is completely different problem. But in this case, we are assuming E less than u naught, right? So if you consider E less than u naught and ux equal to u naught, we can rewrite the expression. We can rewrite the spatial part of the expression, okay? So it will be 2m h line square u naught minus E psi x. So that this is our equation, right? Here this part is positive because u naught is more than E, right? So here I am writing alpha square psi x. So this is positive, means b greater than 0. In the solution we have assumed b greater than 0. If b greater than 0, this will be the solution, right? And if b less than 0, this will be the solution. So here in the first case, when it is inside the potential well, b was less than 0. But in this case, b is more than 0. If b is more than 0, we will have, so I am assuming this equal to alpha square, this part equal to alpha square, okay, alpha square. So if it is alpha square, then we can have the solution like this. Say c, that is one constant, c to the power c e to the power alpha x plus d e to the power minus alpha x, because that is what I have written when I am discussing the uh, general solution, right? When I wrote b, it was like root b. So instead of b, I am assuming alpha square. So that will give me c e to the power alpha x plus d e to the power minus alpha x, right? Now, one point I would like to point out here, I would like to mention here is, so when we are talking about x less than x less than 0, this part, and here energy is u naught, okay, height of the barrier. So you see, when you are moving in this direction, so we are going towards negative infinity, right? Negative infinity. Now, as we are increasing value of x, okay, in the negative direction, you see this term becomes positive. This term becomes positive because there is a negative term here, okay, and we are going negative x direction. So if we increase x too large, okay, and that is in the negative direction, this becomes e to the power alpha x, okay, this negative will become positive and this term becomes very, very large. So as we move towards the negative x direction or very large value of x, okay, so then psi x will diverge, psi x will be very large value, okay, so that is not possible. So we have to consider d equal to 0. So that condition helps us to find out that d equal to 0. So if we move more and more negative, that is more and more away from the well, in the negative direction, then psi x should not diverge, psi x should not be very, very large, okay, because if there is this d term, that is the second term, then psi x will be infinite at negative infinity, right? So that is not possible. So in other words, then d equal to 0. So what will be the psi x in region 2? Psi x is c to the power alpha x, right? Similarly, we can find out, we can find out the solution in region 3, okay. What is solution in region 3? In region 3, that is x greater than L. Here also ux equal to u naught, right? You remember, because in the potential well, this is x greater than L. This region ux equal to u naught, right? And here also E less than u naught, right? So if you use this, you will end up with psi x equal to g, that is another constant, g e to the power alpha x plus h e to the power minus alpha x. Okay? So altogether we have 6 constants a, b, c, d and g, h. Now this among g and h, here also we can argue in a similar manner. Here if we keep on increasing x in the positive direction, okay, so this psi x should not diverge. What does that mean? It means that g should be equal to 0, okay, because when x is very, very large, then this g term, this first factor will make psi tends to infinity, so that can't be the case. So g will be 0. So in the region 3, psi x should be h e to the power minus alpha x. So let me write it the equations now. So psi x equal to c to the power alpha x for x less than 0, psi x equal to a sin kx plus b cos kx for between 0 and l, and c equal to h psi x equal to h e to the power minus alpha x for x greater than l. So this is the general solution for psi, okay, psi x, small psi x. Now we can use the boundary conditions. What are the boundary conditions? You see, at x equal to 0 and x equal to l, what are the boundary conditions? You remember when we discuss psi, we wrote some conditions when we discuss um, yeah. So I can't remember we have written it or not. uh, uh, all I am looking for is the condition I have written for psi, okay. uh, um, Yesterday we have written some condition for psi, right? This is the thing. So psi x should be continuous and del psi del x should be continuous, okay. So this we will use now. So at x equal to 0 and x equal to l, that is the two walls of the potential well, psi x should be continuous, okay. And also at x equal to 0 and x equal to l, del d psi dx should be continuous, because you remember the equation itself contains d2 psi dx to term, okay. So both psi x and del psi d psi dx should be continuous, otherwise d2 psi dx2 will be infinity, right? So we use these conditions, okay, and find out value of c, a, b and h. In infinite potential well, it was much easier. It has only one constant, that is a. I mean two constant, a sin a kx and b cos kx, and we found the value of a and b. Right? B was 0 and a was equal to root 2 over l. But in this case, we have uh, four constants: a, c, a, b, and h. So we can use these two boundary conditions. One is psi x equal to continuous at two walls, and this is also continuous at x equal to 0 and x equal to l, right? So let me write this for you, but then you can, if you are keen, you are young and keen, then you find that C, A, B, H, everything on your own. But let me write the equations, okay? Um, so at x equal to 0, what is x equal to 0? This is x equal to 0, right? At x equal to 0, psi L x equal to 0 is equal to psi r x equal to 0, okay. L is this side, r is this side, left and right, okay, for at x equal to 0. So in the left of x equal to 0, what is the solution? C e to the power alpha x. So I am writing c e to the power alpha x equal to 0, alpha 0, not alpha 0. I'm just writing 0 to make sure that you understand this is x equal to 0, okay. What about psi r on the right hand side? Inside the wells, the solution a sin kx, right? A sin k0 plus b cos k0, right? So this term is going to be 0, this term is going to be 1, so it will give you c equal to b. You see, because e to the power 0 is 1, c equal to b. So this is one using one boundary condition. What about second boundary condition? Second boundary condition at x equal to 0 is first derivative is continuous. Okay, how I will get first derivative continuous? That means psi l star dash is equal to psi r dash 0, right? So what is the derivative? Alpha c e to the power alpha x, right? That is the derivative. So c e to the power alpha x is 0, right? What is the derivative of k sine kx? So that is a ka cos k 0. Okay, and what about b cos kx? B cos kx is minus k b sine k 0. So I am differentiating, right? So you what I will get? Alpha c is equal to ka, because this part is, this second term is 0 because sine 0, right? So this is at x equal to 0. I have used both the boundary conditions. Psi is continuous and psi dash is continuous at x equal to 0 1, right? What about x equal to a1, x equal to l1? At x equal to l, we can have using one boundary condition, left x equal to l, psi right x equal to l, right? So this is right part of x equal to l, and this is left part of x equal to l. So left part will give you what? Left part will give you the solution again that contains sine and cos, right? So left part is sine and cos. So a sine kl plus b cos kl. Okay. What is right part? Right is h e to the power, right part is h e to the power minus alpha x, right? So h e to the power minus alpha l, because x equal to l we are talking about. That is again condition, boundary condition. So 1 and 2. So this is boundary condition say 3. This is boundary condition 4. What is boundary condition 4? Again we are taking the derivative. You remember? So taking the del psi del x will be continuous at x equal to l. So if you take that, you will get k cos k l minus b sine a, sorry, a k, right? B sine, there should be a k term, sorry, b sine k k l equal to minus alpha h e to the power minus alpha n. Okay, so these are pretty straightforward. And then what you can do, you can find out the value of a, b, c and h in terms of one another. Okay, I'm just stopping it here. I will not, if you are very keen, you can try to find out the solution. I'm just telling you the way how you can do it. But let me discuss a little bit further about the waveform. Okay, what is the waveform? Say for infinite potential well, you remember infinite potential well, we got waveform like this, right? E1, E2, E3. So this is for infinite. And for finite, sorry, for finite potential well, okay. So E1, let me uh, so these energy levels in the finite potential well will be lower. Okay, so I am trying to draw, it is difficult. So this E1 should be lower than E1 here, E2 should be lower than E2 here, okay, and E3 should be lower than E3 in the infinite potential well. And what about the wave functions looks like? Wave functions will be like this. Okay. What I try to point out here, in case of finite well, the wave functions at the walls do not go to 0. You see, the wave function here is going to 0. Okay, because it is forbidden. This region is forbidden for the particle to go here because it is infinitely high. Okay, the potential well. So there is no wave function in this forbidden region, and there should, so as I said, like wave function should be continuous, so the wave function here should be 0 also, right? So that is why here it is 0 as well. But in this case the wave function will not be 0 because there is a possibility that particle might be outside the well as well. Okay, even if the energy is lower than that of u naught. Okay, so that is why in case of finite well, the wave functions at the walls do not go to 0. And E is equal to, why I said like E1 is less than E1 here, E2 is less than E2 here, because you see E is equal to H nu or Hc by lambda, right? So as lambda increases, E decreases. Okay, here lambda is more than, here lambda is more compared to that of the finite infinite potential well. If lambda is more, that means E will be less. Okay, that means E will be less. So you see here E1, E2, E3 is lower than that of E1, E2, E3 of the infinite potential well. In classical mechanics, particle can't penetrate the wall if E less than U naught. In classical mechanics, the particles can't go here. Okay, because E, that is the energy of the particle, is less than that of the wall or potential barrier. But in quantum mechanics, it can go to the classically forbidden region. So the wave function can penetrate in the forbidden region, but waves will be exponentially decaying. So here you see waves are exponentially decaying. You remember, that is why we basically remove those terms, right? We didn't consider D, we didn't consider G here, because what we are assuming that the wave will exponentially decay away from the well. Okay, wave will be there, wave function will be there, but the wave function will be exponentially decay away from the well, right? So there is finite non-zero probability of finding the particle outside the well. Higher the energy, more will be the penetration. So so instead of E1, if I go to E3, the penetration will be more, because higher the energy, more will be the penetration. So this I thought that I will just discuss this part. So I am finishing it here today. Do you have any queries? We have few minutes, so if you have queries we can discuss. um, Please remember,
Sir,
we are going to have exam on Tuesday. Yeah.
sir, sir, please
Yes.
share the solution of HCMT solution, sir.
Yeah. HEMT. I will share. Okay. So if you don't hear anything from me by tonight, you drop me a line. Okay. One of you may drop me a
Okay,
line.
sir.
So I have shared these. I have shared mathematical problems. I have shared this whatever I've taught so far. I have shared it already in MS Team. Okay. Right. Anything else?
Sir,
Yeah.
so next week will there be any class? Like in a academic calendar, it is mentioned that that next week there will be no classes.
Why there will be no classes? I am not following that. Um. Uh, there will be no classes next week. There will be no classes. You know the reason?
Sir, in academic calendar, it is mentioned that due to mid semester examination.
What is the academic calendar? So window for test as per regular class timetable schedule. No classes will be held except first year. Okay. Right. Okay. So there will be no class.
Okay, sir.
21 to 25th. Oh, jolly good. So okay. So there will be no class on Monday, but we will have exam on Tuesday from 12, right? Is that okay? Uh, but if you have any doubt, you drop me a line.